This conference will now be recorded.
Hello everyone. Nomenclature for aldehyde and ketones that we have discussed in the last class. Now we'll see some examples based on these rules, and after finishing that, we'll also see how to prepare aldehyde and ketones and some related problems. Here we have some structures, and we have to write the IUPAC name for each of these structures. Okay. So the first molecule here we have aldehyde functionality. So numbering will be started from that carbon, which is basically the carbonyl carbon of this aldehyde group. So this will be 1, 2, 3, 4, 5, 6. So the longest chain is 6, but we have 2 methyl groups at 3 and 4 position. So it will be 3,4 dimethyl hexane, because it is 6 carbon, but it will not end with hex N. It will be hexanal because it is having aldehyde functional group. Second structure is we have keto, not aldehyde. See double bond O, both side there is alkyl group. So it is ketone, so it will end with ONE. And numbering will be started from this carbon, not from the other side, because if you start from the left hand side, then keto group will be given very high number. So you have to do the numbering in such a way so that the position of keto group that will get as minimum number as possible. 1, 2, 3, 4 and 5. So at 5 position there is bromo as substituent, so it will be 5 bromo, and as the longest chain is 5 carbon, so it will be pentanone. It will be ending with ONE. The third structure, here we have 2 keto group, and numbering will start from left hand side. 1, 2, 3, 4, 5, 6. Because if you are starting from the other side, then it will be 3, 5. But in this case, it is 2, 4. So 2, 4 is preferred over 3, 5. So that is why this numbering is correct. Longest chain is having total 6 carbon. So it will be derivative of hexane. And as there are 2 keto group, so it will end with dione. And remember, when there are 2 keto group, that is the term with which we will end, it will be hexane, HEXANE. We have to write the full term and then dione. Now the next structure is we have CC double bond and also aldehyde. So numbering will be started from this position, 1, 2, 3, 4, 5. So longest chain is 5 carbon, and here we have double bond which is starting from 3 position. And here if we consider the CC double bond, whether it is cis and trans, it is cis, or you can say it is Z. So it will be Z3 pentanal. It will end with L because it is aldehyde. Then compound E, we have CC double bond and we also have C double bond O, but numbering will be from this side, 1, 2, 3, 4, 5 and 6, 7. So longest chain is 7 carbon, and this methyl group, it is substituent. Okay, longest chain 7 carbon, so it will be heptane derivative, and double bond is starting from 5 position. Position of keto group is 3. Fine. 1, 2, 3, 4, 5, 6. And 6 position we also have methyl group. So it will be 6 methyl, 5 heptene hyphen 3 one. And the last compound, here we have 2 keto group and 1 hydroxy. So hydroxy, as it is having lesser priority compared to C double bond O. So that is why we will use the prefix for OH, which is hydroxy. When OH is getting higher priority, then the suffix used is OL. But in this case, suffix will be keto, not OH. OH will be treated as substituent. So that is why its prefix will be hydroxy. And as it is symmetry, you can start numbering from any side. It doesn't matter anything. Longest chain 5 carbon, and 2, 4 position there is keto group. 3 position hydroxy. So suffix will come later. First you have to write the prefix, which is 3-hydroxy, then 2,4-pentane dione. So you can see all the names here. The first compound 3,4-dimethyl hexanal. So HEXAN, then E is not written, but instead we have written AL. Second compound, we have one keto group. So this is actually substituent 5-bromo. First you have to write, then 2-pentanone, because the position of keto group is 2. Third compound 2,4-hexane dione. See, try to understand the difference between A and C. In case of A, we have written HEXANE. E is not written. Directly we have written AL after N. But when it is 2 keto group, you have to write hexane completely. Don't omit E, unlike the previous case. After finishing writing hexane completely, then you have to write dione. Compound 4, it is either Z or cis-3-pentenyl. It is pentenyl because 3 position double bond is starting. Then compound E, here we have substituent methyl group at 6 position. Position of double bond is at 5. So 6-methyl-5-heptene. Don't write E, because instead of writing E, you have to write -3-O. That is the position of keto group. And the last compound, again we have 2 keto. So that is why after writing the substituent, which is hydroxy, this is the positions of 2 keto group. 2,4-pentane, write completely. Do not omit E. E will be there because it is 2 keto group. You have to write dione. If it is single keto group, then you have to omit E, and then you have to write ONE or L, depending on aldehyde or keto. But in this case, you have to write the full name of alkane, corresponding alkane, which is pentane, and then dione. Okay. Some more structures. Cyclobutane ring, and 1 and 2 position, there are 2 keto group. So when it is that is ring system, then you have to write cyclobutane. But before that, you have to write the numbers also. 1,2 cyclobutane, then dione. Then the next structure here you have that is symmetrical structure, and longest chain is 1, 2, 3. It is symmetrical. You can start numbering from any side. It doesn't matter. 2-methyl, and 1 and 3 position, there are 2 aldehyde. So 2-methyl propane dial. Propane, it will be PROPANE. Completely you have to write, then dial, because you have 2 aldehyde. So you cannot omit E. Next structure, we have keto group, and we have aldehyde group, and methyl as substituent. We have to give, when both aldehyde and keto groups are there, you have to give priority to aldehyde. So that is why numbering will be started from this position 3, 4, 5, 6. 5 is the position of keto group, and here keto will be treated as suffix. So that is why not suffix, prefix. That is why the term that you will use is oxo, not on. On is used when keto is getting priority, but in this case aldehyde is getting priority, so you have to end the name with AL, not on. Keto group will be treated as oxo, and the position of oxo is 5, position of methyl 3, longest chain is 6. So 3-methyl 5-oxo hexanal. Next compound, again ring structure, we have 2-hydroxy, but these two are actually substituent, right? So cis-2,3-dihydroxy and hexanone. We have only 1 keto group, so hexanone. It is not, you will write, sorry, it is cyclohexanone, not normal hexanone, because it is ring structure. Fine. Then the next compound, here we have aldehyde group attached to the 5-membered ring. We have methyl, we have bromine. And remember, when CHO group is attached to ring system, then this carbon will be 1, not the carbon of aldehyde. That is not 1. The carbon with which aldehyde is attached, that carbon is 1. Fine. Then methyl group, it is 2, this is 3, 4, 5. So 3 bromo, 2 methyl. Now bromo will come first before methyl because alphabetically B comes before M. 3 bromo, 2 methyl. Then it is cyclopentane system. So you have to write cyclopentane, and we know when it is aldehyde group attached to ring system, according to the rule, you have to end the name with carbaldehyde. Next one, it is not ring structure, open structure. We have aldehyde group. This is 1, this is 2, this is 3. 2 position methyl, 3 position bromine. But bromine you have to write first. 3 bromo, then 2 methyl because of alphabetical order, and propanol. So compound G, 1, 2 cyclobutane dione. Cyclobutane write completely, then dione. H, open structure, 2 methyl propane dial. E you have to mention because it is dial. If it is single CHO, you can write propanal, that is PANAL, omitting E, but in this case E will not be omitted. Compound I, 3 methyl 5 oxo. So here keto group is getting less priority than CHO, so that is why it is treated as substituent. So it is prefix. Methyl will come first before oxo because of alphabetical order. M comes before O. 3 methyl 5 oxo and then hexanal. Single CHO, so hexanal omitting E. Compound J, which is cyclic. Cis 2,3 dihydroxy. So 2 and 3, these two positions, there are OH. It will be dihydroxy, then cyclohexanone. So as it is a single keto group, so cyclohexane, not no E is there, then ONE. Compound K, 3 bromo 2 methyl. So this is substituent, this is also substituent, but B will come before M. So that is why bromo you have to write first. Cyclopentane write completely and then carbaldehyde, which is for CH. L, 3 bromo 2 methyl propyl, single CHO group. Fine. So in the previous slide we have seen some structures are there, we have written the name, but now we'll do the opposite, that is names are given, you have to write the structure. A, butanal. Now but, it means it is 4 carbon, ANAL, so it is ending with CHO, so it should be something like this. 4 carbon, 1, 2, 3, 4, very simple. Compound B, 2-hydroxy cyclopentanone. Cyclopentanone, that means cyclic structure will be there. And with respect to keto group, at 2 position there is OH. 2,3-pentane dione. Pentane, see here as it is dione, 2 keto group at 2 and 3 position. So E is not omitted, E is still there. So pentane means 5 carbon chain, 1, 2, 3, 4, 5. 2 position, 3 position, there is keto group. Compound D, 1,3-cyclohexane dione. Now see here E is still there because it is dione to keto group. Cyclohexane system, 1 position, 3 position. Compound D, 4-hydroxy 3-methyl 2-butanone. Here longest chain is 4 carbon. Position of on, that is keto, is 2. So simply write 4 carbon because it is but. 2 position, 3 position is methyl group, 4 position there is OH. Okay. Then compound F, E. E means there is CC double bond. And see it is heptene. In position of double bond is 2. 3 position you have methyl and 4 on. Now 4 on means hept 4, that is 7 carbon, and in the 7 carbon at 4 position there will be keto. 6, 7. Okay. Now 4 position, 1, 2, 3, 4, there is keto group. 2 position there is in. Fine. And 3 position, 1, 2, 3, there is methyl group. Fine. 3-oxobutanal. Butanal, just focus on this part. But, 4 carbon, CHO. So this carbon is always number 1. With respect to this, at 3 position, there is keto group. So keto group with respect to CHO getting less priority. So that is why the prefix we have used oxo, not on. Cis-3-bromo cyclohexane carbaldehyde. Now cyclohexane system, carbaldehyde means CHO group will be there. 3 position with respect to this carbon, because whenever CHO group attached to ring structure, the carbon with which CHO is attached, that carbon is number 1. So if it is number 1 at position 3, that is bromine. And it is cis, that means both, either you write both the bond as solid bond, or that is both are above the plane, or write the other possibility below the plane. Butanediol, but 4 carbon, diol. So just put 2 CHO group both side. Trans 2-methyl 3-hexenal, hex, that means 6 carbon chain you have to write first. 2-methyl, 2 position there is methyl group, 3 position there is double bond. 3 position double bond, suppose this is 3 position, 1, 2, 3, and L, that means 1 carbon there will be aldehyde. 2 position we have methyl group. So trans, okay, yes, trans, which is clear here. This is a trans because larger group are opposite. So now you can see all the structure. So this is the first one, butanal. Then we have 2-hydroxy cyclopentanone, 2,3-pentanediol. Okay. Then D, 1,3-cyclohexanediol. Then we have E, which is 4-hydroxy 3-methyl 2-butanone. 4-hydroxy 3-methyl 2-butanone. Compound F. Now F, it is E, that is the double bond is E, and 3-methyl, position of on it is 2. So it is 1, 2, 3, 4, 5, 6, 7. Compound G, 3-oxobutanal. So this is the structure you can see here, same. Compound H, here I have written both the bond above. You can write the other possibility also, both are fine. Then compound I, butanediol, 4 carbon at 2 terminal position, 2 aldehyde. And the last one, there is aldehyde. So this is 1, this is 2, 3, 4, 5, 6. 2 position there is methyl, 3 position there is the double bond is starting, and 1 is obviously the aldehyde. So in this way, when structures names are given, you can also draw the structure based on the rules that we have learned in the last class. Preparation of aldehydes and ketones. So the methods that we are going to discuss, by this method you can prepare both aldehydes and ketones. And after finishing these methods, next we will see individually for aldehydes there are some methods, individually for ketones also there are some methods. Okay, so these methods are common for both aldehyde and ketone. The first method is oxidation and catalytic dehydrogenation. Catalytic dehydrogenation means what? Removal of 2 hydrogen atoms, that is net removal of H2 molecule. So when you add H2 molecule, that is 2 hydrogen atoms are added, we call the process hydrogenation, and when you are removing it, the process will be called dehydrogenation, and it is mainly done in presence of some metal catalyst. You take alcohol, you remove 2H, it may be 1 degree, 2 degree. See, if it is 1 degree, there will be 2 hydrogen and then OH. So the carbon with which OH is attached, that carbon will be attached to only 1 carbon like this, and this carbon there will be 3 substituents. That's not important. Now if you remove this hydrogen and this hydrogen, what you are getting? There will be a double bond here. So basically now you are getting aldehyde if it is 1 degree. Similarly, if you have taken alcohol, which is 2 degree. That means one more carbon will be attached, only one hydrogen. Now, if you are doing dehydrogenation, or if you are doing oxidation, both are actually it will be same thing, removal of each. Then also you are getting a double bond in this position. But now, as both side there are some carbon-carbon fragment, so this is now ketone, not aldehyde. So when it is secondary, it will be ketone. And if it is tertiary, now reaction is not possible because of lack of hydrogen. Okay. So this method you can find details in the previous chapter that we have discussed, which is alcohols, phenols, and ethers. So when we have discussed the chemical properties of alcohols, that is how we can oxidize alcohols, or what will be the chemical reaction of alcohols when they are undergoing the reaction, that is catalytic dehydrogenation. So the chemical properties of alcohol, you can also consider them as it the preparatory methods for aldehydes or ketones. So details you can find there. Here only the points are mentioned, important points. Oxidation of primary alcohol, you will get aldehyde as it is mentioned in this. I have drawn it here. Oxidizing agents, if you use sodium chromate, dichromate, then potassium permanganate, it may be potassium dichromate also, K2Cr2, PCC, pyridinium chlorochromate. All these oxidizing agents can be used for oxidation. But if you are using intentionally mild oxidizing agent, not strong like KMNO4 or sodium or potassium dichromate, if you are using mild oxidizing agent, then the oxidation will end at aldehyde. So suppose you have started from primary alcohol, as I have drawn here, the first picture. Primary alcohol you have taken and you are using mild oxidizing agent, then the oxidation will stop at aldehyde position, because aldehyde can also further undergo oxidation to carboxylic acid. But that is possible only if you are using strong oxidizing agents like potassium permanganate, Na2Cr27, K2Cr27. Fine. But if you are using mild oxidizing agent, you can stop the reaction at aldehyde stage. Strong oxidizing agent further oxidize the aldehydes or ketones into carboxylic acid. In case of aldehydes, you can when you are using oxidizing agent, it will be converted to carboxylic acid easily. But if it is ketones, then you have to use very strong oxidizing agent, because in case of ketones, as both sides you have carbon-carbon bond, so you have to break CC bond. In case of aldehyde, what you are doing? You are breaking CH bond, but now you are breaking CC bond, which is difficult, and for this only KMNO4 is capable for this process. Okay, and also here number of carbon atoms will be decreased because CC bond is broken. Fine. And let me erase all this. Okay, details actually I have not mentioned here. You can check this chapter, alcohols, phenols, ethers. When vapors of alcohols, so up to these first 3 points are related to oxidation, and the fourth point, it is for catalytic dehydrogenation. If you are passing vapors of alcohols, which is basically the starting material, over heavy metal catalysts such as copper, silver, then alcohols will give aldehyde, and that is primary alcohol, and secondary alcohol, if it is present, it will give ketones by dehydrogenation process. So either you use oxidizing agent, then also you are getting aldehyde or ketone starting from alcohol, or you can use another method, which is catalytic dehydrogenation. You have to use some heavy metal catalyst. Fine. Second method is ozonolysis of alkenes, and in the previous case, alcohols are the starting material for preparation of aldehyde and ketones, but now alkenes are the starting material for the preparation of aldehyde and ketones. And as we have mentioned, ozonolysis, so obviously we will use here the gas ozone. What we do in this process, alkenes react with ozone gas. First it forms ozonide, which is a cyclic type of structure, but this is not the end product, which on subsequent cleavage with reducing agents such as zinc and water, zinc is actually the reducing agent, you get aldehyde or ketones. Depending on what type of alkenes you have taken, you can get either ketone or aldehyde. Now here the role of zinc dust is to remove H2O2, which will be produced as a byproduct. Because if you are not removing this H2O2, then it can oxidize the aldehyde and ketones. But we do not want the H2O2 to act as oxidizing agent, because our purpose is to make these aldehydes and ketones. Obviously, we do not want the H2O2 to oxidize this. So that is why you have to remove this H2O2 somehow. And for this, we use zinc dust. Here we have examples. We have started from this alkene, which is but2ene, 4 carbon, 1, 2, 2 position, there is double bond. Now this CC double bond will be broken, but first there is formation of ozonide, which is ring type of structure. This ozonide, if you just imagine as if there are two fragments, so from the left hand side fragment, what you are getting, CH3CH, there will be a double bond formation. So one CH3CHO, from the other side also you are getting another CH3CHO, because it is symmetrical ozonide. Fine. So see, ozonide, when it is finally we are breaking it, we are using this ZnH2O. So here this oxygen is extra. You can think as if it is H2 and O, it is making H2O2. And this H2O2, if you are not using Zn, it can further oxidize CH3CHO to carboxylic acid. But we want this compound because we are synthesizing it. So that is why zinc should be used to remove H2O2. Then the second example, now it is just like the previous example. The only difference, now it is not symmetrical and you have methyl group, as if this H is not present now, now you have methyl group. So same ozonide, only this methyl group is extra. So from left hand side part, it is same as the previous structure. So again, you will get one acetaldehyde. But from the other part, now as you have methyl, you will get acetone or propanol. Fine. So depending on what type of alkene you have taken, you can get either aldehyde or ketone. And as it is mentioned here, if it is terminal olefin. Now what is terminal olefin? When we are saying terminal olefin, it actually means CC double bond, one double bond if there are two hydrogen attached to the carbon. Other carbon, suppose there is R group. But the right hand side carbon, it is basically terminal olefin. This type of olefin where you have one CH2 fragment. So from this, what you will get, just think, if you are breaking this CC bond, from this part you will get RCOR. Obviously, if you are using zinc and water in the second step. Remember, it is specifically the reaction that you are seeing here, only if you are using some reducing agent, then only you can get this type of product. But if you are breaking this ozonide ring by using some other condition, that is oxidizing agent, obviously products will not be same. But that is details you don't need to know. Just remember, if you are using reducing condition for breaking the ozonide intermediate, then this type of aldehydes or ketones you can get. So when you are using zinc and water in the second stage, then obviously from this part you will get OC double bond C HH. So when there is terminal olefin, you will get from the terminal CH2 position, you will get formaldehyde. Right? So this is the second method. Now we are going to third method. Third method is hydration of alkyne. Alkyne means CC triple bond will be there. Okay. As we are saying hydration, that means it is net addition of H and OH. So see here the reagent we are using water, and RC triple bond CH, we have taken terminal alkyne. It is a general structure of terminal alkyne. Why we are calling it terminal? Because right hand side you can see we have one H. So that is why it is terminal. So the reagent combination that we use in this reaction is water, obviously, because it is hydration. Then H2SO4 acidic condition, and we need Hg2 plus ion as a source. So the source is mercuric sulfate, HgSO4. And here H2O, first there is addition of H and OH, but that structure is not written because first you will have this type of enol structure. OH is added. Now CC double bond will be there, not triple bond. Then H and another H. Now this is enol type of structure, and this enol, it will be tautomerizing finally to ketone. So that is why you are ending with methyl ketone. Why we are calling methyl ketone? Because this group we do not know what group this is. This is general, but this side you have CH3CO group. So that is why you are calling it methyl ketone. But the intermediate is, you can see here OH in the enol structure as if it is addition of H and OH to CC triple bond. That is net addition of water molecule. But this enol, it will be finally converted to ketone structure by ketoenol tautomerization. Hydration of alkynes require a strong acid, which that is for that purpose we usually take sulfuric acid, and also mercuric ion should be present. Hydration of alkynes, it gives ketones, but remember, except acetylene. So when it is acetylene, it is actually AC triple bond CH. So in this case, you cannot get ketone. But except this acid alkyne, this is the simplest alkyne possible. But for the other structures, that is, except this structure, for all other alkynes, you will get ketone. Okay, before going to the actual example, let's also see. This is the first possibility where one side you will have H, another side you will have some alkyl group. Now the second possibility is symmetrical internal alkyne. It is internal because you do not have any H both sides. That is why we are calling it internal, and it is symmetrical also. Both sides same R group is there, right? Same condition. So first there will be addition of H and OH like this. But finally this enol, it will be converted to this type of keto structure. And you will get only one type of ketone because you have same R group both sides. If it is not same R group, two possibilities are there. If OH is added towards left hand side carbon, you will be end up with this. Suppose if it is R and R prime, then the keto you will get RCO CH2R prime, right? But if OH is added to this carbon, another possibility is RCH2 COR prime. But in this case, as it is symmetrical, we will have only one type of ketone. Then the third possibility, now we have different R group, so mixture of ketone products we will get. Now see actual examples. Ethyl, that means acetylene. So when it is acetylene, then an intermediate enol structure is written here. After isomerization, ketoenol tautomerization, which is a kind of isomerization, then it is like this. This OH bond will be broken, CC bond broken. So negative charge over left hand side carbon. So this H, it will now come to left hand side. So finally we will be getting this type of structure, that is H, CH. So this is nothing but ethanol, or you can call it acetaldehyde, whatever. So you are now ending with aldehyde. But once you have added one R group here, for example, this one, prop 1 ine. Why prop? 3 carbon, number 1, 2, 3. 1 is the position of ine. So name is IUPAC name prop 1 ine. Now in this case, as it is not symmetrical, the first addition of H and which these two fragments, it will be according to Markovnikov rule. So see, this carbon is containing lesser number of hydrogen. So that is why the negative part of the reagent, which is basically in our case HO, the negative part, HO minus H plus, if you break water molecule, the negative part of the reagent will be added to that carbon which is having less number of hydrogen. So that is why which is added to left hand side carbon, which is number 2 carbon. This is number 1 carbon, this is 2, this is 3. So 2 carbon OH is added, 1 carbon H is added. After isomerization, what you will get? You will get propanol. So it is never, it never occurs, that is other possibility you will never get. What I mean by other possibility is, if OH is added to 1 carbon, this is another possibility, right? But this will never happen. If it happens, then you will get, after tautomerization, CH3CHO. Sorry, CH3CH2CHO, like this. The tautomerization, so equilibrium sign. But this never happens. Never happens. So you will only get propanol, because the first addition of H and OH from water, that is based on Markovnikov. Fine. Based on this hydration of alkyne, we will now discuss this problem, which is saying which one of the following carbonyl compounds. We have 4 carbonyl compounds mentioned in option 1, 2, 3 and 4. Which of these cannot be prepared by addition of water on an alkyne in presence of HgSO4 and H2SO4? So it is not directly mentioning that it is hydration of alkyne, but when it is mentioned addition of water on an alkyne in presence of Hg2 plus an acidic condition, it is nothing but the previous reaction, that is hydration of alkyne. Fine. So among these 4, which one we cannot prepare by this method? That is the question. Fine. Now what we have seen in the previous example, that first there is a triple bond, you add water, there is addition of H and OH according to Markovnikov, and finally there is ketoenol tautomerization. And CH3CHO, this molecule we have already prepared. Remember, CH3CHO we have already prepared from ethyne. That means you can prepare this molecule, right? Then the second molecule, cyclohexane system C double bond O CH3. Now this molecule, if you want to prepare, then what type of alkyne you will take? You will take cyclohexane, then C, then triple bond CH. So this type of alkyne you will take as starting material. So OH will be added to this carbon because it is containing lesser number of hydrogen. H will be added to the right hand side carbon. So you are getting this enol structure. After tautomerization, you will end up with this. So 2 also we can prepare. Now if you want to prepare this, what type of molecule you will take? Obviously this type of molecule. But this example, third example, you have already seen in the previous slide, that is this one. Remember, CH3 C111C. So in this molecule, whenever you will take for this reaction, you will always end up with acetone, because the other possibility CH3 CH2 it will never form, right? Because you get only one enol, so its formation is not possible. That means CH3 CH2 CHO. If this is your desert compound, you cannot prepare by this method. So here correct option will be option 3. So whenever you will take this molecule, you will end up with acetone or propanol. So 3 molecule we cannot make by this method. You have to take the help of some other method. You can take CH3, CH2, CH2H. That is propyl alcohol, linear chain propyl alcohol. You can use oxidizing agent and you can prepare this, but not hydration of alkyne. Okay. And the last one here, 4 carbon and it is ketone. So you can prepare it if you are taking this type of alkyne. So it is symmetrical structure, no problem is there. OH and H added to this is a triple bond, and then there is ketoenol tautomerization. Fine. So correct option, option 3. Number 4 method. From calcium salt of carboxylic acid. Salt of carboxylic acid, what it means? Carboxylic acid is RCOOH, right? Now this H, as it is acidic, if I am writing the corresponding metal salt, if suppose the metal is sodium or potassium, valency 1, then just remove this H and you can write Na or K. But if it is calcium, now it is from group 2, its oxidation state is 2+. That means Here it is sodium plus 1. So that is why part CO2 minus, you can place 1 in. But when it is Ca2 plus, now it will be RCOO, calcium. Then other side also, there will be another same fragment, right? So now it is the calcium salt of carboxylic acid. You can prepare aldehyde or ketones by dry distillation of this type of calcium salt of carboxylic acid. Okay. Now here we have example. What salt we have taken? We have taken calcium methanoate. That means, look at this part, HCOOCA. That means it is salt of formic acid, or you can say salt of methanoic acid. Just remove this H, place Ca. Another fragment also you have to add because it is 2+ oxidation state. So this is the structure of calcium methanoate, or you can write calcium formate. So if you are starting from this molecule is the starting material, you are doing dry distillation, then what will happen? See, here some dotted line is given so that you can understand that this Ca, 1 carbon, 3 oxygen together as if it is making CaCO3 as a byproduct, and this part is remaining HCO, another H, so it is making formaldehyde or methanol. So when your starting material is calcium formate, then the product will be aldehyde. Now in this case, we have taken only 1 calcium salt, right? You can also take 2 calcium salt. See in the next example, in the right hand side we have taken again the same molecule that you have taken in the previous case, calcium methanoate or calcium formate, but the other structure we have taken another salt which is calcium ethanoate. So as if it is, just look at this, it is CH3COH, acetic acid. Just remove the H and place C. So if you have taken mixture of this type of molecule and just focus on the dotted part, here we have Ca, then CO, as if this is 1 CaCO3 and this is another CaCO3. So if you are removing 2 CaCO3, now you are left with CH3, CHO, CH3, CH. So you are getting 2 acetaldehyde molecule. Okay. So in the second point it is mentioned aldehydes will be obtained if one of the salt is calcium formate, and if it is that is if you have not taken mixture, you have taken only calcium formate, then obviously it will be aldehyde. But when it is mixture and in the mixture one of the salt is salt of calcium formate, then you will end up with ethanol, because here from 1 calcium salt this fragment you will always get, and whenever this fragment is there, both side of CO, if you compare one side, there will always be 1 H. So aldehydes you will get if one of the salt is calcium formate. If you have you want to make symmetrical ketone, you just not want to make ketone, but you want to make symmetrical, both side of keto group there will be same group, then what you will do, you can do dry distillation of calcium salt of carboxylic acid except formic acid, because whenever you will take one of the acid as formic acid salt of calcium, it will always be aldehyde. But if your purpose is to make ketone, you cannot take calcium salt of formic acid. So here our purpose is to make acetone or propanone, and for that purpose we have taken calcium ethanoate only, that is this molecule, but we have not taken any mixture, only this part. So as if you remove the dotted part in the form of CaCO3, you are now left with CH3CO and CH3. Just add these 2 fragments, you will get CH3CO, CH3. Based on this, we have this question: by combining 2 calcium salts of carboxylic acid, we are preparing 2-butanone. 2-butanone means this structure. So you are trying to make 2-butanone, which is basically ketone. And in the previous slide, what we have seen, if your purpose is to make ketone, you cannot take one of the salt in the mixture, you cannot take calcium formate as salt. So based on this information, you can easily cancel option A and D, because here mention of calcium formate. So one of the salt cannot be calcium formate, right? From another point of view also you can compare it. See, in the previous slide, you have only one carbon in the final product. Here you have two carbon, right? So when you have started, as one carbon is removed in the form of carbonate, that means if in the final product carbon number is n, then in the starting material carbon number must be one extra, because one carbon will always be less in the form of carbonate it is removed, right? So if you apply this logic also, and here in the ketone you have how many carbon? Total 4 carbon. But in calcium format you have one carbon. In propanoate, prop 3. So 3 plus 1, it is 4. This is also 4. So it is not n plus 1 and n. So this is not possible. Then D also it is 1. Acetate means 2. So now total carbon is 3. But in the final you have 4. So this is not possible. Now option B, if you see, calcium acetate 2 carbon. This is calcium propanoate 3 carbon. So 2 plus 3 5, and here it is 4. So this may be correct, right? And if you see option C, calcium acetate 2 carbon, this is also 2. 2 plus 2, this is 4. So from 4 you cannot get 4. It will, if you are starting from 4, it will be 3 the final. So based on this, you can choose the correct option. And here we have all the examples. The first one, calcium formate and calcium propanoate, you will end up with propanal. Okay. And the second one, that is actually the correct option. Just you can also apply the logic. If you are in a hurry, you do not have time to write all these equation, it's fine, no problem. Just apply the logic that 2 plus 3 5 carbon, final product 1 carbon less. So this may be correct option, though it is always better if you can write the equation. But if you are in a hurry, lacking in time, then also you can apply this trick, right? So option B correct. Then option C, you will end up with acetone. 2 calcium acetate molecule, you will get 2 acetone. In the previous slide also this example is mentioned, but there only 1 calcium acetate is taken, so you are ending with 1 acetone, but here you have taken 2, so 2 molecules of acetone. And D, calcium formate calcium acetate mixture, if you take, you will be getting acetaldehyde. So B is the correct option. After finishing the common preparatory method for aldehyde and ketones, now we are starting preparation methods for aldehydes only. First method is Rosenman reduction. So as it is saying reduction, so we have to use some reducing agent. Aldehydes can be prepared by hydrogenation of acid chloride. Acid chloride is prepared from carboxylic acid. If carboxylic acid is RCO2H, the corresponding acid chloride is RCOCl. So you have to take this type of molecule, and reducing agent is palladium in presence of barium sulfate. Here barium sulfate is basically catalytic poison for the catalyst PD. So actual catalyst is palladium. It can be asked that in Rosenman reduction, the mixture of PD and BaSO4 that you are using, in this mixture which compound is actually the catalyst? So here the catalyst is the metal PD, palladium, and BaSO4 is acting as catalytic poison. Now what is catalytic poison? Sometimes it may happen that the catalyst that you are using that is so reactive that you will end up with a product which is not your desired product. So in this case, you are starting from RCOCl. Your purpose is to make aldehyde. But suppose if you are not using BaSO4, you are using only PD and H2, you can end up with some other products also. That is, further reduction can also be there. That is, further reduction if it is occurring, you will end up with RCH2H. But that is not desired. We do not want it. So you have to control the reactivity of PD. You have to make it more selective. It is very reactive. So you are ending up with more reduced product. But that is not wanted, not desired. So that is why you have to use some other compound which can control the catalytic property. the reactivity of PD, and that is why it is called catalytic poison. That is, it is hindering the effect of the catalyst. So that is why the name catalytic poison. So if you are using this mixture, you will end up with aldehyde at aldehyde, not further reduction. But by this method, you cannot prepare formaldehyde. Though we are discussing it under preparation of aldehyde, and formaldehyde is also aldehyde, but you cannot use for this, and obviously not for ketones. Here we have taken the first example is general example. So these are group of RCOCl. Here it is benzene ring. PHCOCl. So it is derivative of benzoic acid. PHCOOH. Just remove the OH, place Cl. It will be benzoyl chloride. In presence of H2PDBSO4, you are getting benzaldehyde. Next method, Stephen's reaction. In this case, the starting material is alkyl cyanide. When alkyl cyanide are reduced, reducing agent essential to HCl. First, there is formation of imines, C double bond N. But imine is not our desired product. We want aldehyde because this is preparation methods of aldehydes. So the imine intermediate, after when it is formed, you have to do hydrolysis. Then you are getting the actual product, which is aldehyde. Alkyl cyanide general structure you can write as RCN, but here we have taken CH3CN. In presence of essential to HCl, first there is imine. So here the imine you can also write it in this way, CH3CH double bond NH. But as here in the medium we have HCl, so this NH, there is lone pair, it will be protonated, another H will be there. When it is protonated, it is positively charged, counter ion is Cl minus. That is why it is written in this way. Finally, we are doing hydrolysis. The fragment NH4Cl will be removed. You will be getting CH3CHO. So this O, as if it is coming from oxygen. Okay. So this C double bond N, it will be broken. There will be O, and this H, these two H, and there is H also in water. All this will be removed in the form of NH4Cl. Okay. So starting material RCN, if I write general, you are ending with RCOH. Okay. Examples, more examples. Cyclic structure, the R group here is cyclopentane ring, CN, but you have to just focus on this part. Rest of the part there is no change. R group is pH, this is intact, only CN is converted to CH. Number 3 method, reduction of cyanide and also reduction of ester using a reagent which is known as DIBAL, DIBAL. The full name of this molecule is diisobutyl aluminium hydride. Look at this molecule, isobutyl. First you have to understand what is the structure of isobutyl. Butyl means simple linear chain 4 carbon. But when we are saying isobutyl, the structure will be like this. This is also 4 carbon because there is a methyl branching. So this is one isobutyl, this is another isobutyl. So 2 alkyl group and aluminium valency should be 3. So 2 alkyl group, 1 H. Diisobutyl aluminium hydride. This H is hydride, H minus. So it is written as dibal H, sometimes simply as dibal or DIBAH. Okay. So this reagent, it is used as a reducing agent. Dibal partially reduces nitriles to imines, unlike LiAlH4. Now, if you are thinking that why we will use dibal, because there is another reagent, very good reducing agent, lithium aluminium hydride. Why not use that? But the problem with lithium aluminium hydride is that its reducing capacity is so high, it will reduce nitrile all the way to amine. That is, nitrile is RCN. So it will end up with amine, but that we do not want. We want the reaction to stop at aldehyde, not at amine. So that is why we have to use a reducing agent which is not very reactive. It should have reactivity but not like LiH. So that is why we are using here diol. The imine are then hydrolyzed to aldehyde. So first there will be formation of imine. Then there is, just like you have seen in the previous reaction, essential to HCl, there also first imine is produced, then you are doing hydrolysis, you are getting aldehyde. Same thing here. So unlike LiAlH for lithium aluminum hydride, it will not reduce aldehyde further if only one equivalent is added. So you can control it. If you are you want to prepare amine, you can use another equivalent. So see, we have taken RCN in presence of diol H. That is the first step. And in the second step, we are using hydrolysis acidic condition. You are ending with aldehyde. So this is also RCN to RCHO. Initially forms an imine which is then hydrolyzed by acid. Very interesting fact is that, look at this example here. In this starting material we have CC double bond, we also have CN, but this reagent diol, it is written here not as diol but in a different way, but same reagent. So this part is intact, only CN is reduced to CHO. So you can do this type of selective conversion also. If you have taken ester as starting material, then also you can reduce it to aldehyde. But in this case, you have to keep the temperature very low. It is only especially for esters. So you have taken this ester C, Me2CH, CO2Me. You can also write it in this way, Me2CH, COOMe, same one. But it is ester. This is ester group. You are using this reagent. This is solvent. And very low temperature hydrolysis. Low temperature is important here to prevent further reduction. So when it is low temperature, that means you are providing less energy. So as there is less energy, further reduction to some other compound is not possible. Okay, so it will be stopped at aldehyde position. So that is why this low temperature is necessary. So in the next class, we will start preparation of benzaldehyde and also preparation methods exclusive for ketones. So these three methods that we have seen, the last one is using diol and the previous reagent Rosenmund, PDBSO4 and Stephen. These three methods are for aldehydes. So we will end the session here. Thank you for listening.